Thank you very much for the nice introduction. And of course, since I've been in the last few years interested in catalysis and also specifically in the haber-bosch process, it was very nice this morning to visit the museum, which I recommend you do too. Huh? It's a very nice experience, as you know. The main the glory and the tragedy of this person. It's a larger than life character, besides being a great scientist. Okay, so we're gonna talk about catalysis today, which I think I got my degrees in physics a long time ago. I never thought I would ever had to work on catalysis. Okay, but there you go. Life is complicated, and this path is somehow so Langevin-like. So why are we interested in catalysis? And of course, the need of having energy efficient catalytic process is crucial to developing a green economy, among other things, of course. But I mean, you want to generate hydrogen, capture CO2, and so on. And I stress, you want to do all these processes on an industrial scale, like Bosch did, because if you do in small quantity in your lab, it's of no use. I mean, you get a publication, but it's no use to mankind at large. Okay, so if you look at the chemistry book and you think how they describe catalysis, it's essentially a static view, in the sense that if you look at the potential energy surface, there will be a stationary state as a reactant and product here, and you go climb a hill, go through the transition state, and go on the other side. And catalytic object is something which is able to lower this transition state, as is shown here. Okay, and most of it is based on chemical intuition, and dynamics is only described most of the times at harmonic level. Okay, now let's go upstairs, and you see the reactor that have been used by Bosch and BASF, and that's like that can be as the reactor can be as large as 30 meters long. So, and reactor work at high temperature, like 400 Kelvin, which happens to be the temperature of a pizza oven. And at high pressure, in fact, most of the technology that Bosch developed had to do with dealing with high pressure processes. Okay. And then if you consider that, is it possible that a simplified description that you have the active site to look for, and that's the problem is solved? Good enough? Of course, to have this active site is crucial. But how can you explain that this reactor, this catalyst, remains stable for years? I think if you took a catalyst that Bosch used and you put in the reactor, it would still work. How is that possible? After having been in the reactor and under this hellish condition for decades. Okay. And experimentalists that work more closely to the real life, they had doubts about this simplified version, and they describe scenarios which could be could explain what is observed. This is it was already long time ago. Spencer, who worked for an industrial company, then he said that when you have a catalyst operating, you set up a stable quasi-equilibrium condition, which is a bit like when you have a thermodynamic thing. You change the temperature, the system goes liquid or solid. It depends on what you do. And that's what happens. So it's stable. Anytime you change the temperature, it happens. So you want a situation where you set up conditions which are stable relative to the flux of incoming reagent and product. In more modern terms, Robert Schlegel, to whom I owe a lot of my understanding of catalysis, he talks in more modern terms. And I mean, practical catalysts are usually heterogeneous because engineering, from the engineering point of view, that's very much simpler than homogeneous catalysis. Because if you have homogeneous catalysis, at the end you have to separate the product, that can be very costly. Instead, you have a heterogeneous catalysis, say a surface, the reactant come here and go away. And so it's much simpler to have a continuous flow. You don't have to stop in principle if you run forever. Okay. And then he argues, I mean, this paper is very interesting. There are many things which are, although he hasn't done a single calculation. All this comes from his doing experiment and being in contact with chemical companies, okay? And they say, well, if you have a heterogeneous catalyst, the surface is not a static, it's a platform for reaction. So when you have active sites, and that's it. They are dynamical entities that evolve and form active sites with the reactants under reaction conditions. So it's a very dynamical view, okay? So can we say something? Can we do a simulation that can back up or give insight of what really is happening? One of the problems is, of course, that experiments are difficult, because they take place at high temperature and high pressure. And only now, with the experimentalists are able to do experiment approaching that, what they call, it's called operando conditions. So can theory come to the rescue? And that's what is my talk. So the tool, the natural tool, from the point of view of simulation, would be to use ab initio molecular dynamics, where you describe the force from first principle. You take into account of the change in electronic structure. And so if you have bonds that are formed or broken, as it happens in a reactive process, then you can deal with it. But the problem is that it would be too expensive to do that. If we simply took the code, say Parrinello, WASP, whatever, and there are millions of different codes that in principle can deal with that, but they are too costly. But in the last few years, there have been progress in the technique, mostly based on the use of neural network. And let's so I think we were with Jörg Beller, who is now in Bochum. We were among the first to use the idea of to apply the idea of using the ability of neural network to represent a complex function of many variables to do what to do. I mean, people in machine learning don't like this notion, but do a fitting and so what we did is to do a set of ab initio calculation on a different number of configuration, and we train a neural network to reproduce as best this data. Or as they say in the jargon, to generalize this data. Okay. And machine learning has made enormous progress since those days. And now there are packages which are relatively easy to use, but for training the neural network and also for running ab initio. In particular, we use DeepMD, but there are many other alternatives. So that's one facet of the problem. The other problem is the time scale problem, because reaction take place on a time scale which we simply took our system and we ran it for a while, we wouldn't see anything. So we need a way to accelerating the time and go from the very short time scale that you can afford with atomistic simulation to the long time scale. Okay. And so we have developed method to help with that. And we don't have time to go into that, but basically the gist of this thing, this method, is that we try to identify the slow mode of the system, which we call collective variable, and we amplify the fluctuations it's important to, in a statistical mechanics compliant way, so that we can get equilibrium properties, and we look at the free energy. So we move from potential energy surface with free energy, and so in so doing, we bring into the picture the entropy. Okay, so method that we look a little bit into that is a method. There are millions of methods. Also our chairperson here today, she's has developed a very interesting method to solve this problem. We do with I'll come back to that. So, but these are methods based on identifying this collective coordinate. And so we have why did I bring it to the attention? Because the way how we construct a potential for a reactive process. So we started doing a small initial molecular dynamics. We add, we train the first guess for the neural network, so that's it. Then we want to see reaction. Okay, so we use some of this enhanced method to get the new, to collect a new configuration, and we go into this cycle until we have a potential. Okay, so one of the issues of this method is to do this efficiently, because if you have to calculate the millions of density functional calculation, that's you defeat the purpose. You want to reduce the number of initial calculations you want to do, also maybe to get better DFT calculation. So there are many ways of improving that. One is to use a data efficient architecture, equivalent neural network, transfer learning. So then we can use foundation model, or we can do data selection schemes on the flight. And so this I report on his work done in my group, but not by me, but Luigi Bonatti. So he asked himself, so if I do a calculation here, this is the molecular dynamic calculation, how many points do I need to get a potential that's good? So one would reduce the number of initial calculations in that way. And so on top of it, what happens when you have a reactive process, you start with the reactant. And at the beginning of calculation, you don't really know where you're going to go. So you're trapped in a minimum and you want to get out. And so the way they do is they use a method that is called flooding. So I'm here, I do a bias calculation, I let the system get out of this trap, and systematically harvest a number of reactive pathways. Okay, so, and that's the way it goes. So this is talking of Bosch. This is a nitrogen molecule on top of a surface. And here we have a simulation where we start when it's blue, it means it's accurate. When it's white, it means it's not accurate. So they have a way based on Bayesian approximation to calculate the probability, the uncertainty of the prediction that you make. And we follow here in this graph here, the process in which the bond length of the nitrogen molecule is grown until it grows. So the way the method goes is that we do the system, the molecule begins to oscillation, begin to grow. We say, okay, so this is our limit uncertainty I can accept. So I go here. So I start my simulation. I watch for this uncertainty of prediction. Whenever it goes out, I add, I make it stop the calculation and make a density function calculation. I continue, then I go up, and then whenever needed, I add a configurations. So the way so this is an example. Again, it's a realistic, it's not a model. That has to do with the haber-bosch process. So first iteration, I get a better potential, I repeat it, and as I repeat, the number of initial calculation decreases all the time. And eventually I can get reduced by orders of magnitude the number of DFT calculations. So this is an important process that is progress. So, and here I try to get reaction, one reaction, dot reaction, until I sort out the energy, the description of the reactive process. Okay. Okay, so these are the methods that we use and that allow to, I think, to overcome. And see, I'll share with you some application. Our interest for several years has been in trying to apply this method to the haber-bosch process. And that's a very, of course, for mankind, is a very important process because you can do fertilizer. So it has helped reducing the world famine. But it's not cheap because it consumes about 2% of the total world energy supplies, and it is environmentally very damaging. So it is also very complicated, and I will not talk about it today, but people are also looking at alternative to the haber-bosch that can be environmentally more friendly. And I consider a very recent proposal to use this compound, barium hydride, which sounds very unlikely compound from the point of view of catalyst. And I consider this among the main examples because it's contained, so it's a finished study, and also it's an illustration of the idea that I described of Schlögel as the catalyst not being a passive thing, but being part of the reactor. The whole catalyst, in this case, you will see, of the whole barium hydride is a catalyst, not the surface, not one atom, not two atoms, it's the whole system. And so that's very instructive from the point of view of how we think about catalysis, or particular industrial catalysis. And so some years ago, actually it's very recent, a few years ago, a Chinese group reported this result. They, for some reason, which in retrospect they must have thought of, but because barium hydride is an ionic compound. Catalysts are typically metals that are able to give electron and take electron, and that's why they're catalysts. But anyhow, so they decide to try, for whatever reason, barium hydride. And they made two experiments. In the first experiment that they put together, exposed the barium hydride to nitrogen and hydrogen at the same time. Nothing happens. Nothing happens. But then they decided to do a looping process where they first start with nitrogen, wait a bit, and then they add the hydrogen in a looping process. Actually interesting. If you start with hydrogen, it doesn't work. You have to start with nitrogen. Okay. So this seems to us like a very promising example of this experimentalist view. So that you start adding nitrogen, and that changes the nature of the system so much that something that is inert then becomes a catalyst. Okay, so let's, to give an idea of what we can do these days with this new method, I'll go into some detail with this catalyst, because there is some interesting physics, chemistry. So, as I said, this system, this kind of catalyst, you cannot understand them unless you have a global view of the system. And so we have to become familiar with the system. And so this is, as I said, an ionic compound, crystallizing the system, and the hydrogen can be tetrahedral or octahedral. And it is important, the ability at high temperature of the hydride to move. That's what is called a superionic compound. Okay. As you increase the temperature, you form vacancy in the system. Hydride have the tendency of losing hydrogen molecules. So also this barium at high temperature loses a few hydrogen molecules. But then if you lose 2 hydrogen molecules, you're left with, you have to replace the neutrality of the system, because you had 2 H minus, form a hydrogen molecule, you have to leave behind electrons. The electron sits in cavity, and that's what is called the electride. And these cavities will be the source of electron in the catalytic process. Okay. Because of the vacancy, so that's the first ingredient. Electron can be localized in the system. Second ingredient, atoms can move. Huh? So both anions, at low temperature, nothing happens. But when you go to high temperature, H minus becomes superion. So if this, both ions and electrons can do funny things. Then the barium, nothing much, at the low temperature, and a few things at high temperature, but even high temperature, the motion is very limited. So the structure of the barium is not perturbed. Okay, but in this case, it is interesting what happens to the surface, because barium loses hydrogen. What is the mechanism by which a barium loses this reaction? So see, they come together and the hydrogen evaporates. Again, since the two hydrogen evaporate, there are two electrons that are left, that are produced. Where do these electrons go? They go into the surface to form this surface state. And the surface state, the energy of the surface state is very low. So the HOMO is the Fermi energy. The HOMO, so yeah, this thing goes, two electrons are here, and these are not neutral. This is a system, electrons that are easily, since they are at the Fermi level, easily given to the system. So no, sorry, I got it wrong. This acts as a Lewis, what is called in chemistry, Lewis's basis, not using acid, okay? So now you have this surface where you have this Lewis's basis floating about, and then you send it a nitrogen molecule. And of course, what happens is that what molecule goes spontaneously into where the basis is in case structure and forms this compound. And if you look at the chemistry, it has to stay horizontal, and that's what happens. And step number one. That's step number two. The system is full of H minus. And one of these H minus can attack this molecule, which is already weakened because there could be electrons. So, and form this intermediate. And then there's another step, which is also interesting. I will not go into the details, but the chemistry goes on. It's very, very interesting. So you can add a proton to this compound. So at the end of this process, what have you done is that, so if you follow this reaction, is the two H minus in the system are replaced by one amide, this compound. So that's what happens. And then I got by two amides. I mean, it's full of mistakes. Sorry, I apologize for that. So, but that's not the whole story. So that's what happens on the surface. So I've started with something which is added this nitrogen, and now I'm enriched the system with the imides. And these imides, they don't stay on the surface. They move and they permeate the whole system. Huh? So at the end of the nitrogen exposure, you have a different system. You have this mixed system, which is made of BA, the original BA plus this imide, all over the place, all over the place. So this is the catalyst. So the function of N2 is to take a system which was not was simply barium hydride and make it into this complicated system, which is a very good catalyst. Because now, you see, and this thing can go all over the place, okay? So the catalyst doesn't get poisoned, because if all the imide stayed at the surface, it would quickly be poisoned, but it goes all over the place, and both imide and hydride, they can move like crazy inside. Huh? So we are ready to expose the system to hydrogen. Huh? And that's the best. Now it becomes very, very, very easy. Huh? The first hydrogen, and then another hydrogen. And your little ammonia goes and is used for whatever purpose. So to summarize the complicated thing here, so we warm up the barium hydride. We transform at high temperature, this becomes an electride. Then I expose it to nitrogen. Through a series of processes, I end up with a different compound from what I had before. And in this compound, it's very easy to hydrogenate the system. And once you get the N, all the N are gone into the ammonia, you go back to here, and you can continue and continue. Okay, so some of the steps are experimentally verified. So that's things that for which we have experimental backup. One interesting similitude, if you think of the strategy that the catalyst follows to break the N-N bond. N-N bond is very strong. It's a triple bond. And Haber got the Nobel Prize because he managed to break this bond for the first time artificially. But nature does through a very complicated enzyme, which is called nitrogenase, and which has also, it's a mind-boggling series compound, complication, also the architecture, but what is done in nitrogenase is rather than breaking at the first step, the N2, it starts to add electron, then to add protons, 1, 2, 3 protons, and until the bond is so weak that it breaks. And then you can add more protons. And so rather than starting immediately like Haber, breaking the N2 bond, you start weakening one step at a time. Okay. This is not the only, we have studied many systems and like all connected to the ammonia economy. In particular, this is to ammonia cracking because ammonia, people want to use ammonia to transport hydrogen. So all the time, there is something very similar that happens, a profound change in the nature of the catalyst. Okay, so okay. Catalyst is not associated to a static arrangement. but out of equilibrium, but steady in, I would say, interfacial dynamical study. And this explains the long time of industrial catalysts. The interfacial catalytic state can be induced by temperature or by reagents, or both. And I think a new theoretical tool needed to describe such a state. Okay. So since we are here, and there's Rebecca has an interest, like many of us, into enhanced sampling. So that's I want briefly describe some new way that we are studying to, we are proposing to do the enhanced sampling story. Okay. So if you look at metadynamics and many other methods, essentially what you do, you have the original potential, you add the bias, an extra potential, an external potential, such that you fill the wells. So you artificially change your system. So in the modified system, the system can easily go from one well to the other. What if you, rather than filling, you dig? So you go from A to B, you have a mountain, you get rid of the mountain. Okay. So you can go from one to the other. But this is easily said, less easily done. Huh? How do you do? So we're going to use a concept, which is a committer, which is much used in what transition path sampling literature. What is this mysterious object? Okay, the committer is a function that gives the probability that the trajectory started here, ends there without passing by A. And now, if you try to figure out how this committer is done, so if I'm here, and the barrier is high, I have a very little probability of going there. So here the probability is 0. On the other hand, if I am on the other side of the valley, it's very easy. It's highly probable that I go. So it's a function that in A is 0, in B is 1. And there's a region where you go from 0 to 1, which is the transition state region. It's the difficult bit when you have to go over the mountain. Okay, yes, but why are you bringing this notion now? What is the meaning of doing this? One of the reasons is that, I say, when in doubt, you look at the Russian mathematicians for solutions. So this gentleman, Kolmogorov, and I think this paper was written during the war, so it must be, it's interesting, it's written in German, and I think by Kolmogorov himself. So for foreign people like me who have a difficulty with the German, it's not so difficult to read in the original. And he found this remarkable result that these dynamical things that seem impossible to calculate, in fact, can be the solution of a partial differential equation. Okay. And to solve this, there is a variational principle that allows you to compute, in principle, the committer. And I write this here. I take the gradient of Q, which looks something like that. Because here 0, here 0. It's all focused on the transition state. And I solve the variational principle under the boundary conditions. And incidentally, this gives you the rates of transition from A to B, if you are in a Langevin kind of scenario. Okay, so we have made progress from solving a partial differential equation, which is multidimensional, impossible to solve, with a variational problem that looks somehow simpler. But if I look at the integrand, I see much of the contribution comes from this transition region, which is understandable because that's a reaction. A reaction depends on the transition state. Okay, so, but this is the region we don't know how to study. But if we were able to get a committer, we would be home and dry, because we had the bias, which is like this. Forget the thing. So this is a minimum in the transition state region. So if I add to my original potential this bias, this with suck configuration in the transition state by its very nature. Okay? And so this bias, okay, so, but that's a chicken and egg problem, because if I have a committer, I can get information on the transition state. Huh? But to get information on the transition state, I need a committer. So how do we do? So we set up a self-consistent procedure that we start with the guess, which can be even purer for what the committer should be. And then we use this first guess, we get more configuration and so on and so forth. So just to give an idea how this works, what I do is so this is a toy potential, which is called Mueller potential, which has one minimum here, one minimum there. Then I do two simulations, one in A, and I collect the blue, one in B, I collect the red. And then I say, okay, so my first guess, okay, thank you. My first guess, the committer, is something very simple. I want the committer to be 0 here and 1 here. So I can also classify. You got the machinery of neural network, a great classifier that tells me that I put the label 0 in the blue and the label 1 in red. And he makes this prediction for the value of the committer 1/2. This is the exact value. So I use the first poor guess, and already after one iteration, I find that my guess has already improved, and I go quickly to the solution. And the solution, you see that I get lots and lots and lots and lots of data on the transition state. So this is a fantastic way. I don't have time to go into the details. It's a fantastic way of studying the transition state. Okay, just again to do some problem which is closer to the interest. So I showed a potential, which is very simple, but we are doing a real problem. So, for instance, to study the automatically the reaction mechanism of malta-pentose, which is, that's it, that should be a movie. Truth. We should improve the quality of the movie. This goes to a transition state region until the reaction spontaneously takes place. The ring is closed. The other thing, the other example is HIV protease. Again, just it's a machine that works on its own and very, very quickly gets you to the right result. Okay, so that's just to give you a taste of what might be the consequence of this new approach. I would like to thank all the people in my group. It's really extremely good. Sudeep has done the calculation on the enzyme. Luigi I discussed in detail. Umberto and Axel have worked on the barium hydride. Palin and Enrico are responsible for this new exciting, in my eyes, I mean, that's so so there is a saying in Italian, which it's not easy to translate, but basically means even the ugliest of babies is beautiful in the eye of the mother. So my thing, this theory at the moment looks very beautiful to me, and I thank you for your attention.